Hello, my name is Carlos Casares. I'm a mechanical engineering student at the University of Maryland, College Park. This summer, I conducted research in the Vibrations and Acoustics Laboratory with faculty advisor, Professor Kenn Oldham. The goal of my research was to analyze the walking dynamics of millimeter-scale microrobots through numerical simulation in order to see what parameters are the most important in determining walking speed. First, we look at a conceptual design for a walking microrobot. This is a complex dynamic system with many degrees of freedom. In addition, there are nonlinear foot-ground interaction forces that become significant at this small size scale. In order to more easily analyze this walking robot, we make several simplifying assumptions. First, we assume that motion is constrained to two directions, vertical motion in the z direction and horizontal motion in the x direction. The distributed mass and structural parameters of the body and legs are represented by an equivalent lumped parameter system. Each set of legs that moves together is represented by an equivalent foot mass, mf, connected to the body mass, mb, by a spring with stiffness k and damping coefficient b in the horizontal and vertical directions. There is an actuation force between the body and each foot that drives one foot down and back to propel the body forward, while the other foot lifts off and moves forward. The dynamics of the horizontal and vertical system do not affect each other unless a foot contacts the ground. In this case, Coulomb friction determines whether the foot sticks or slips horizontally. We determine the equations of motion for the system using Newton's second law, which dictates that the sum of structural force due to the stiffness and damping of the legs, the actuation force, and the external force is equal to the inertial force. There is an equation of motion for the body, foot 1, and foot 2 in both the horizontal and vertical directions, giving 6 equations total. We numerically integrate the equations of motion in order to simulate walking dynamics. For each time step, the forces on foot 1, foot 2, and the body are accumulated according to the left-hand side of the equations. We then check conditions to determine whether contact or stick events occur. Next, we compute the positions and velocities at the following time step by numerically integrating calculated accelerations on the right-hand side of the equations. The simulation output shows a steady-state walking gait. The output statistics that we are interested in are the walking speed and the average body height. We use the engineering technique of dimensional analysis to systematically determine the parameters that influence walking speed. This technique allows us to reduce the dimensional parameters in the simulation, such as masses, forces, and distances, to a fewer number of non-dimensional parameters. Changes in these non-dimensional terms fully describe changes in the output, which is non-dimensionalized walking speed. There are several interesting trends in walking speed that result from varying the non-dimensional parameters of the simulation. First, if we vary the horizontal damping ratio, which is a non-dimensional measure of energy dissipation in the horizontal direction, we observe that low horizontal damping results in faster walking speeds. This trend is especially pronounced when the actuation frequency matches the horizontal natural frequency. This trend can be viewed in the stride trajectory of foot 1 at the dash frequency. As the damping ratio decreases, step size increases, which causes an increase in walking speed. If the vertical damping ratio is decreased too much, then resonance in the vertical system can cause large amplitude oscillations. These large vertical oscillations can cause missed ground contact on some strides, which results in significantly slower walking speeds. Another important factor in walking robot design is actuation requirements. If the vertical actuation force is too small relative to the weight of the robot, then the body does not lift off of the ground. If the actuation force is too large, then vertical motions can cause missed foot contact and reduced walking speed. The effect of small-scale foot-ground interaction forces on walking speed was negligible, except in the case of adhesion. If adhesion force increases too much relative to the actuation force, then the pull-off force at time 0.5 is smaller than the adhesion force, which causes the foot to stick to the ground and deviate from a normal trajectory. All of the discussed trends are non-dimensional and therefore can be applied to a wide range of robots with different sizes, materials, and structures. The results of the walking simulation will be used as design guidelines for the development of high-performing walking microrobots. If you have any questions about the research presented in this video, please contact me at this email address. Thank you for your time.